let's have a look at the scope and the limitations of the Grignard reaction. So we said that you can perform Grignard reactions with aldehydes, with ketones, with esters, but there is quite a number of functional groups that we can say they are incompatible with the Grignard reaction. So you cannot have, for instance, a reaction of a ketone simultaneously having an alcohol or an amine or a thiol or a carboxylic acid. So what is the problem there? Well, the problem is that all those are functional groups that they have relatively acidic protons, those hydrogen atoms that can be donated rather easily. And that means that the very strong delta minus that we have in the alkyl group in the Grignard reagent. And so that will react with the proton source of the alcohol, amine, or thiol, etc., or even worse, the carboxylic acid. And all what will happen is that you will form the RH, and that will be the end of the game. So in other words, you are destroying your Grignard reagent. So we said functional groups that will traditionally we use for synthetic purposes. We can use aldehydes or ketones, and McMurray didn't put here esters as well. You can have an RCOOR. And remember, in the case of the ester, you will have to use two equivalents of the Grignard reagent. So let's see these following reactions, and you tell me, is the reaction going to work or not? So here, what are we trying here? We intend to have a reaction of the ketone with the Grignard reagent, one equivalent of the Grignard reagent. We are using the proper solvent, ether. But what is the problem? Well, the problem is that the molecule that we are trying to react, it contains an alcohol. So that will be a no-no. And that means that there will be no reaction. There will be no successful reaction. Or what I will obtain, it will be that this portion of my Grignard will become this, will become propane, and my and then I will have no addition of the alkyl portion into the carbonyl group. There will be no reaction at all. So that will be unsuccessful. How about the next one? Okay, we are using a good Grignard reagent. We are using ether, good solvent. But again, here we have a carboxylic acid. So even before I will have the CH3 minus to react with the carbonyl group, before that, the proton of the carboxylic acid will be donated. The CH3 minus here will capture that proton, and I will end up with formation of methane. Big failure, that's right. How about the next examples here? So here I have an alcohol that actually is an alcohol that was transformed into a tosylate. That is a good strategy, right? In other words, we can say that the tosylation of the alcohol is serving as a sort of a protection of the alcohol functional group. So in that case, yes, I would expect that I will have a successful reaction. So I will still have my tosylate here. And then the aldehyde, being an aldehyde, I should obtain a secondary alcohol, right? And so this is going to become an OH, and then I'm adding a 2-carbon atom unit. There is my 2-carbon atom unit, right? And so that will be the final product. And then perhaps I may consider a reaction that would allow me to remove the tosylate part and in that way I can get back my alcohol, right? Later on, we will learn another method that is even better for protection and deprotection, and that is using the trimethyl ether. And so that will be toward the very end of chapter 17. And there we will learn this method of protection and deprotection. How about the next reaction here? Now we have a ketone that we are trying to react with ethyl magnesium bromide. But attention, here I'm proposing that the solvent that I want to use is ethanol. No, that is terrible, right? Ethanol, CH3, CH2OH. There I have an acidic proton, so again the reaction will not be successful. All what I will get will be formation of CH3, I will have formation of ethane, and my cyclohexanone will not react at all. Well, so let's have a look at the mechanism of the Grignard reaction. So the mechanism is simply a reaction of the alkyl anion, we can say. I say that you have a very strong delta minus, so strong that we can consider for all purposes, when writing down a mechanism, we can consider this as being a carbon ion, right? And so that in the simplest case, it could be a CH3 double dot minus. So you have nucleophilic attack on the carbonyl group, and then we have the oxygen will take care of the additional pair of electrons. So now here in the intermediate, in the alkoxide intermediate, we have 3 lone pairs of electrons on the oxygen, and then a pair of electrons of the alkoxide will capture a proton from H3O plus, and we will have protonation of that. And so here, notice I'm using a color code here. I am using the R minus, so that is the one that is being added to the carbon atom of the carbonyl. And then I am using in green here the proton that is coming from the H3O plus. That is the one that appears in the final product. So notice the similarity between the reduction mechanism and the mechanism of the Grignard reaction. So in the case of the reduction, so we have the hydride. This is the hydride. The hydride anion is acting as a nucleophile on the carbon atom of the carbonyl compound. We have formation of an alkoxide, and then the oxygen of the alkoxide captures a proton from H3O plus in the second step of the reaction. And that gives you the final product, alcohol. It could be a primary alcohol, a secondary alcohol, or even a tertiary alcohol, depending on the carbonyl compound that I have used as a starting material. In the Grignard reaction, we have attack of the carbon ion, formation of an alkoxide intermediate, and then in the second step of the reaction, protonation of the alkoxide to get again a primary, secondary, or tertiary alcohol. And so very, very similar reactions and very similar mechanisms. In one case is a hydride, in the other case we can say is a carbon ion, the one that is attacking the carbonyl group. Okay, so reactions of alcohols. Well, this is a reaction that we got to discuss in chapter 11, right? I believe in chapter 11, when we discussed the SN1 mechanism, we use this as an example. So if you have a tertiary alcohol, tertiary alcohol. So in that case, the HCl may provide a proton to protonate the alcohol, and we form this water molecule that is a good leaving group. If we are dealing with a tertiary alcohol, the departure of the water molecule actually will not be so much of a trouble, because when the water molecule leaves, that will give rise to a carbocation that is tertiary. So tertiary carbocation, we know that tertiary carbocations are fairly stable. And then the Cl minus that left here, we had the Cl minus that departed. So that can come back here, and it will add to the carbocation intermediate from one side or the other side, and that will give you as a final product an alkyl chloride. If you have used HBr as a starting material, as one of the reagents, so in that case, the product you will get will be a corresponding bromide. But we said if the alcohol that we want to react is a primary alcohol or a secondary alcohol, the use of HCl or HBr is not such a great idea. Why? Because after the departure of the water molecule, we will get a secondary, or even worse, a primary carbocation, and those are not very stable. So that's why in those cases we propose that the best approach is to use thionyl chloride instead of HCl. Thionyl chloride, there is the structure of thionyl chloride, ClSOCl. Obviously, the sulfur is a good electrophilic center. So there you can have nucleophilic attack of the alcohol on the sulfur. Momentarily, you will get this intermediate here. You will get this intermediate. And here you can see that at this point we can regenerate the sulfur oxygen double bond, and we get departure of a Cl minus. So, and that will form this so-called chlorosulfide intermediate. A chlorosulfide intermediate, it has a very, very good leaving group. We can form a sulfur oxygen double bond here, and then we have departure of a chlorine, and in that way we form, notice that we have a proton here that is being eliminated, and we have a Cl that is being eliminated. So that is what is forming HCl, right? All right, so I will stop here because I don't want to go beyond 14 minutes.